We're going to begin section 10.3 today, which is applied properties of chords. If you remember from section 10.1, the definition of a chord is a segment whose endpoints are on a circle. So here, this is chord RS. For today, we're going to use the phrase, the arc RS is an arc of chord RS. The arc RS is the arc of this chord. We have a theorem that says in the same circle or congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So if I have congruent chords, I can put them anywhere in the circle. That's sort of about congruent there. If these are congruent, then the minor arcs that go with them must be congruent, and vice versa. So here, these lines, I'm going to draw in the central angles that go with each of these chords. And what we know about these, we're going to look at these triangles here. What we know is that all four of these segments are congruent because they are all a radius of this circle. And if these four segments are congruent and these chords are congruent, it means that these triangles are congruent. The triangles are congruent, all the corresponding parts are congruent. These central angles must be congruent. So if these central angles are congruent, remember, say this was x degrees and this is x degrees, we know that the measure of a minor arc is equal to the measure of the central angle. And now I have two arcs that have the same measure and are in the same circle, so they must be congruent. We can prove it the other way, starting with the arcs being congruent and working backwards to the chords as well. In the same circle or congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. A couple comments here. A diameter always splits a circle into two semicircles. Every other chord has a minor arc and a major arc, and you'll notice in the theorem it refers to the minor arc of that chord. We can also have a midpoint of an arc. Y is the midpoint of arc XZ if arc XY is congruent to arc YZ. If these two arcs have equal measures and are on the same circle, so they are congruent arcs, then Y is called the midpoint of arc XZ. Any line, segment, or ray that contains point Y bisects the arc, just like any line, ray, segment, or plane that bisects a segment is, or that contains the midpoint is the bisector of the segment. Another theorem. If one chord is a perpendicular bisector of another chord, then the first chord, so let's see, if one chord is a perpendicular bisector of another chord. So here's my chord, and I'm going to make another chord that is the perpendicular bisector of that chord. Perpendicular bisector, so it has to go through the midpoint and be perpendicular, and I'm going to draw that as best I can here. Go through the midpoint and be perpendicular. And what we see is that when you have the chord that is a perpendicular bisector of another chord, that first chord is always a diameter. There's our perpendicular bisector. A related theorem, if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. If we know that this diameter is perpendicular to this chord, so say this is A, B, X, Y, and Z. If we know that diameter XY is perpendicular to chord AB, then it must go through the midpoint of AB. So AZ must be congruent to ZB, and arc AX must be congruent to arc XB. One more theorem. In the same circle or congruent circles, two chords are congruent if and only if they are the same or equidistant, the same distance from the center. Two chords are going to be congruent. Let's again try to draw them congruent to each other. The only way that they can be congruent is if they are equidistant from the center. So remember, if we're doing distance from a point to a line, it must be measured on a perpendicular. So these two distances are going to be congruent if those chords are congruent. If AB, chord AB, is congruent to chord CD, then they are equidistant from the center, from point O. If we look at these diagrams, it says, what can you conclude about the diagram? Here, we're told segment AB is congruent to segment CD. What can we conclude? AB, and we can conclude that the arcs are congruent because we have a theorem that says congruent chords have congruent arcs. We could also say those chords are equidistant from the center, but the distances aren't drawn in the picture. Here, we have a circle, and we're given 140 and 140 are the measures of arc AB and arc CB. If those arcs are congruent, then congruent arcs also have congruent chords. So we would know segment AB was congruent to segment BC. In this picture, we know that this segment is a diameter because it goes through the center, C, and it is perpendicular to the chord AB. What does that tell us? It tells us that it must bisect the chord. So AD is congruent to BD. Also, if we added a name for this point on the circle, we also know that that arc has to be bisected. So AX, arc AX, must be congruent to arc BX. In each of these problems, O is the center of the circle, which means we know that, for example, OT is a radius. S, down to the bottom, is a diameter. Here, we want to find the length of segment RT. When you have a diameter that is perpendicular to a chord, it always bisects the chord. So if MT is 15, RM is also 15, making the length of RT 30. Then we want to find the length of OM. This is a right triangle with a leg of 15 and a hypotenuse of 17. You can use Pythagorean theorem, or that's one of our Pythagorean triples, 8, 15, 17. If we have OM, we could then find MS. It would be 17 minus 8 to give you the rest of that radius, and so on. Here, we are given the one arc measure from A all the way around to B. That's a major arc. The first question asks for the measure of arc AB, which refers to the minor arc from A going to B. So we're going to take 360 minus the 220 gives us an arc measure of 140. Then I want to find the measure of arc AC. What we see here is O to C, that's a radius, which is part of a diameter, that is perpendicular to the chord AB. So it has to bisect the chord and the arc, which means each of these arcs must have a measure of 70 for them to add up to 140. Then we want the measure of angle AOC. Angle AOC is a central angle whose intercepted arc has a measure of 70, therefore the central angle is also 70. In this diagram, we want the measure of arc CD. What we have is this is circle O, and that O should be over here. And we have these lengths, which are equal to each other, and also really need to have perpendiculars here. If these lengths are equal and are perpendicular to the chords, we know these chords are equidistant from the center. If they're equidistant from the center, the chords are congruent, and therefore their arcs are congruent and have to have the same measure. We have to have those perpendiculars there in order to be able to do that problem. Last example, we're going to start with circle O with radius 12 centimeters. I'm going to make that my center O. Make a circle with that center. We're going to say the radius of O is 12 centimeters, and we have chord RS that is 6 centimeters from O. How long is the chord? We have a chord RS whose length that is 6 centimeters from O. So we're going to draw the chord, and the length from O, the distance from O, has to be along a perpendicular. Chord RS is 6 centimeters from O, so this length is my 6 centimeters. This is circle O with a radius of 12 centimeters. So the hint with all circle problems is when you feel like something's missing, add a radius to an important point. In this case, I can draw the radius from O to R or from O to S. They would be congruent to each other, obviously. That radius is 12 centimeters. What we want to find is the length of the chord. If we look at this triangle, it's a right triangle where the hypotenuse is twice one of the legs. You could do Pythagorean theorem, or you may recognize that when the hypotenuse is twice the leg, that's a 30, 60, 90, and the 6 must be the shorter leg. Shorter leg times square root of 3 gives you the longer leg. That's the distance from R to this midpoint. We then have the same distance on the other side. So the length of the chord RS must be 2 times 6 square root of 3, which is 12 square root of 3 centimeters.